Welcome to today's video. We're going to do examples of Fourier Transform. We're going to understand better the Dirac delta and what does it have to do with the Fourier Transform at all. We're going to also take a look at the uncertainty principle, and while doing also, we're going to try to get a little bit more understanding of what the Fourier Transform really is. Okay, remember the Fourier Transform, we always talk about, okay, we have a variable, could be time or could be position, whatever. It takes us from that domain to the frequency domain. So what is that? It tells me the frequency spectrum of a function. How many different frequencies make up a function? So you would imagine that if you have a cosine of omega t, then the frequency spectrum should be non-zero only in one point. And we will see that because there's only one frequency. If I have, let's say 3, right? If I have only the cosine of 3, if this is f of t, whatever the Fourier transform is, in k, should be 0 for all k except for when k is equal to 3, or perhaps when k is equal minus 3 as well. Other than that has to be 0, and maybe we'll have something here, but I don't know what it would be. If I add another cosine of t, for example, that's frequency 1, well, maybe when k is equal to 1 and minus 1, there would be something here, but nothing elsewhere. If I write a function, say that my function is a constant, like f of t equals 3, like that. How many frequencies does it have? Well, this thing is a constant. It doesn't change in time. It does not oscillate. Therefore, the Fourier transform should be 0 everywhere except for something as 0. It's got 0 frequency components. Anyway, this is a little bit of intuition of trying to understand the Fourier transform as the frequency spectrum of a signal, of a function. As we will see later on, we're going to be gaining understanding on that as we progress. Let's begin with something like that. The Fourier transform of a square function. Now, this one is kind of a constant, but then suddenly goes to 0. So whatever the Fourier transform is, it should have a lot of 0 frequency component, right? Because there's a lot of constant in this function. But then it should contain a lot of frequencies because it does vary. So everything that varies contains higher frequencies in the Fourier transform, higher than 0. 0 frequency is slow variation, and 0 exactly no variation at all. And the faster a function changes, right, and the more it changes, then the higher you would expect the frequency spectrum to be for large values of k. Anyway, let's check that one and see what we get. All right. So a is larger than 0, of course. Let me just write a larger than 0. I didn't specify, but it makes little sense otherwise. Okay, so the first thing that we're going to do is apply the definition. Remember, the definition of the Fourier transform, f of k is 1 over square root 2 pi minus infinity to infinity. D of t dt, f of t, e to the I kt. Now, in our case, it's rather easy if I substitute, because the integral from minus infinity to minus a is 0, because the function is 0 until it hits minus a, and then from a to infinity is also 0. So in this case, the Fourier transform is just 1 root 2 pi integral from minus a to a dt of the function that is 1, in that case, between minus a and a, so it's just e to the I kt. And an integral is very easy, it's the integral of the exponential, the most difficult integral ever. The result is 1 over root 2 pi, then 1 over ik, which comes from integrating the exponential ikt from minus a to a. Now, of course, this is 1 over root 2 pi. Let me have 1 over k here, and then put the I in here, e to the I k a minus e to the minus I k a. All right. Now we recognize this. Remember, cosine of x is equal to eix plus e minus ix divided by 2, and sine of x it's equal to e to the ix minus e to the minus ix divided by 2i. Okay, well, this is almost the sign. In fact, it's twice the sign. Anyway, I can put a 2 in here. I can put a 2 in here, which is doing nothing. So this results into 1 over, well, I'm going to have it 2 over root 2 pi So I'm gonna write like this, sine of Ka divided by K, using the definition of the sine. Now we can simplify this, of course. Let me just write it here. This is the root of 2 over pi sine Ka divided by K. Now, commonly, we write this in terms of the sinc function. What is the sinc function? I don't know if you've heard it before, maybe not, but it's a very famous function, so it's good that you know it because it's used notation-wise. We define the sinc of x as the sine of x divided by x. That is the sinc function. It's very famous. It's called sinc function. Right. So this sinc function here, if I write everything in terms of the sinc function, I have square root of 2 over pi times a sinc of Ka. Okay? And that's the result. That's f of K. Now, if we were to plot it to see what this is in the frequency spectrum, we would get, this is f of K, this is K. We get that this thing is maximum, the sinc function, the sinc at 0 is 1. You know that, right? The sinc at 0. So let's check. What is the sinc of 0? Well, it's the limit, I'll write it like this. The sinc of 0 is the limit when x goes to 0 of of sine of x divided by x, and then you see that this is 0 over 0, so we need to do a limit to compute it. Doing a Taylor expansion, that's very easy because the sine of x is x plus things of higher order, so it's x over x, which is the limit when x goes to 0 of x over x, which is just 1. So the sinc at 0 is 1. So the height of this thing here is a with a factor root of 2 over pi, right? So this thing is like root 2 over pi a. And the same function is like a sine, but it's modulated by a linear decay, right? So what we get as a function of k is something like this. Right, let's do it like that. Ooh, and symmetric. It's symmetric. All right, my drawing skills are not that good. It has to make it symmetric. Something like that. You can ask Wolfram Alpha to plot this function for you. Right. So this same function tells me, the Fourier transform of k tells me that the square, this is the function in the time domain if you want, or in the position domain, and this is the frequency domain. So you can tell that the frequency k equals 0 dominates. After all, it's a lot of constant stuff in here, not a lot of variation. But then the fact that it suddenly drops makes it contain all the frequencies a little bit and decaying slowly as the frequency goes to infinity. Very slowly decay. It's like 1 over k kind of decay. All right. Let's see another one, and let's see examples where we can compute it using the properties. All right, let's do another simple one. All right, I collected the first example, f of x here, and the Fourier transform here. Let's do another example. Fourier transform of now the same one, but with a equals 1. Now you see it's 1 from minus 1 to 1. That's pretty simple because it's a particular case of that one, so I can write the solution directly without doing anything. There's no fun in that. I make a equals 1, 2 over pi, sinc of k. There you go, that would be the solution. Now another way to compute it is using the scaling property of the Fourier transform. Because that is actually more fun and allows us for a double check that with the rescaling property we're applying it right and we get the right result. Okay, so we know the result already, but let's get it from our rescaling as well. All right then, so we know that g of x is a rescale version of f of x. In particular, is f of ax, right? You can check that when f of ax, right? If I get f of x and I multiply the variable by a, I get exactly g of x. It's a compressed version, and I'm compressing this thing, which is amplitude to a, to amplitude 2, okay? By scaling by a factor of a. All right, if we apply the scaling property, then we get that g of k, which is of course the Fourier transform of f of ax, because that is what g is. That is just 1 over a capital F 1 over A, absolute value, 1 over F of K over A. Right, now we know that A is a positive number anyways, so let's see, I write 1 over A because it's a positive number. Now F, which is this guy, but evaluated at K over A, so whenever I see a K, I write K over A, so it's root of 2 pi A sinc of K over A times A. Alright, A is cancel, and the result is 2 over pi sinc of K, which is exactly the result we got when we particularize this to the A equals 1, which is what this function is. So double check that the scaling property, we know it, and we use it right. Alright then, let's do another example. This new function is 1 if x is between 0 and 2a, and 0 otherwise. So what is this? This is the same function as we have here, only that now it is displaced to the right by factor a. So we know that h of x it's actually f of x minus a. Just displace me to the right by a units. Then we can use the shifting property of the Fourier transform to compute it. And what we get is the following. So h of k, which is of course the Fourier transform of t minus a, it's equal, remember the shifting property of, the Fourier transform of f of t minus a. This is curved bracket, okay? Then this, the shifting property tells me that this is e to the k a f of k. Alright, so I just substitute and I get square root of 2 pi e to the I k a sinc of ka. And that is the result, that is h of k. As simple as that. Alright, so we see that the spectrum, the frequency spectrum of all of them is very similar. It's the same function centered at 0. This one has a complex phase. In general, the Fourier transform is complex. But if we check the modulus, the magnitude of the function still piles up next to 0 because this is almost a constant. We're not going to compute many more Fourier transforms in this course with the definition and so on, because there's no much point in it for what we want to learn. But let's go to slightly more interesting notions. Let's revisit now the Dirac delta, shall we? Let's go there. Okay, the Fourier, I call this the Fourier representation of the Dirac delta. Let's see, I have here as a reminder the definition of the Fourier transform and the definition of the inverse Fourier transform. Now, question, let's go ask an innocent question. What is the Fourier transform of the Dirac delta of t? Remember, if we were to plot this function, the Dirac delta of t would be a function that is 0 everywhere, peaks at 0 to infinity actually, but the integral of it is 1. Remember the delta, right? We have a video on the delta, Dirac delta, and maybe there's a card somewhere here. I don't know. Maybe. Alright, so the Fourier transform of the Dirac delta. Well, let's just substitute. So we get that this is 1 over 2 pi integral from x infinity to infinity dt delta of t e to the I kt. Right, but the integral of the delta times something, so remember, the delta, if I have the integral from minus infinity to infinity dt of delta t minus t0 f of t, the result is evaluate the function at t0, right? Now here t0 is 0, so what I get, oh, I'm missing the square root, sorry, okay? Then what I get here is 1 over square root 2 pi e to the I k0, so that thing is equal to 1 over root 2 pi. Huh, the Fourier transform of the delta is a constant. Alright. Okay, so what I'm going to do now is I'm going to apply, so let me just write this equation here. Right, we found this. let me apply inverse Fourier transform on both sides. If I do that, well, let's just do all the steps. F minus 1 of f of the delta of t, inverse and Fourier cancel, equals to inverse of 1 root 2 pi. Aha! So what I get is that delta of t is equal to the inverse Fourier transform of 1 over root 2 pi. Or in other words, this is 1 over root 2 pi, the Fourier transform inverse of 1. All right, but let's write the definition then. Let's write the definition of the inverse Fourier transform there. Delta of t is equal to, substituting this definition, root 2 pi and root 2 pi gives me a 2 pi, 1 over 2 pi, integral from minus infinity to infinity of dk e to the minus I kt. Ha! Very interesting. Not only that, in fact, this is the same. I can do the change of variables k to minus k, right? And k to minus k gives me, k is equal minus k. So dk is equal to minus dk. So the change of variables k to minus k swap the limits of integration, but I get an extra minus sign from the differential of dk. So overall, what I get is 1 over 2 pi integral minus infinity to infinity. We can call this one tilde, dk tilde e to the I k tilde t. And then because it's a dummy variable, it's like Joshua, then I can remove the tilde, and that's right. The delta function is an even function, doesn't matter the sign of t. Delta of t is equal to the delta of minus t. Now, this thing here is what we call the Fourier representation of the delta. Now, this is kind of cool. The delta is, the Fourier transform of a constant to begin with. And second, we can understand the delta of t. This is the important part of the definition, right? Let me just write it here. Delta of t, I can understand it as 1 over root 2 pi, minus infinity to infinity dk exponential of IKT. The integral of this exponential minus infinity to infinity is what I call the delta. Now, let's really think about this, because this is strong. This is really strong and very like, what? In many ways that I don't know if everybody will see the first time they see it. Let's reflect about it. If we were mathematicians, learning mathematicians, I imagine that we started to learn about calculus, right, as mathematicians, we would be, right. Somebody defined the Fourier transform, which is here. Now, for this integral to exist, for this integral to be convergent, not anything goes, because, this, when t goes to infinity, the exponential of IKT becomes, well, remember, the exponential is the cosine of kt plus I sine of kt. In the limit t going to infinity, that becomes infinitely oscillatory, right? It's oscillating like that forever. There's no limit. When you take t to infinity, those things don't have a limit. Just keep oscillating, right? So we better make sure that this function is good enough so that it cancels those oscillations in time. In particular, the condition for the Fourier transform to exist is that f of t is what we call an L1 function. What does that mean? That actually means absolutely integrable. Or, in other words, this is the same as saying that the integral from minus infinity to infinity of the absolute value of f of t dt is not divergent. That guarantees that this implies that f of plus minus t has to go, plus minus infinity, has to go to 0 for that to be well defined. Alright, so you see, if this doesn't go to 0 at infinity, there's no way that it's going to be non-divergent. So that means that very few functions, so there's a subclass of functions that would have Fourier transform, and those are the functions that somehow decay. It can be like constant here, whatever, but eventually have to decay. Now you see, the Fourier transform of 1, or the Fourier transform of x, or if f of x is x, or f of x is 1, those functions are not absolutely integrable. In principle, a mathematician would say they have no Fourier transform. And indeed, the Fourier transform of 1 is something like this, multiplied by root 2 pi, but it's something like this what you will get, and that integral does not exist. If you try to do this integral, let's see what happens if you try to do it, right, in the usual way. This integral, minus infinity to infinity, dk e to the I kt, well, that is the integral, it's 1 over I t, right, e to the I kt from minus infinity to infinity. But from k equals, the integral over k equals minus infinity, or goes to, if you want, and k goes to infinity. And what is that? Well, this thing doesn't have a limit. When k goes to infinity, it just keeps oscillating. It's a cosine and a sine. Just keeps oscillating. This thing does not exist. It's not a convergent integral. Mathematicians, when they're learning only the concept of functions or calculus, those things are not well defined. In principle, there should not be a Fourier transform for it. And there isn't as a function. You see, the delta, remember, is not a function. We saw it. It was pretty outrageous. Remember? Again, I'll display the card again. Or not. I mean, if I really figure out how to do it, I'll display the card here. But you see, the delta is not really a function. It doesn't exist as a function. It's pretty outrageous. We saw it. It's like 0 everywhere, then infinite, then 0, and then the integral is 1. And it's just sudden, in a point, it's infinite. Yeah, exactly. That thing that is not a function, that does not exist, can be, so now we can use it the opposite way. This integral that doesn't exist as an integral, as a function, that doesn't produce a function of t, we say, yeah, I know, but it produces a distribution, and it's the same distribution as the delta. This is kind of cool, because it allows us, that's why I never told you what are the conditions for the Fourier transform to exist. Because we're gonna actually not respect those conditions, because we're extending the Fourier transform outside when the integral is well defined, and we have that, and this is actually a way to define what this integral is, and how this integral acts. This is literally the delta. And it's a way to define the delta as well, and you will see it used like that many times. So that's kind of cool, because that means that I can also define the Fourier transform of x, the Fourier transform of t, if you want. What is the Fourier transform? Let's do it. What is the Fourier transform of t? Well, as a function, it doesn't exist. It's the integral minus to infinity t exponential I kt. That is divergent. That doesn't exist. Using the definition, I get 1 over root 2 pi integral minus infinity to infinity dt f of t is t e to the I kt. Now, of course, this integral does not exist. This integral is divergent. It doesn't exist. So if I'm looking for a function, there isn't any. This doesn't have solution as a function. But is it a distribution? And the answer is yes. Let's see what we can do. We realize quickly that t e to the I kt can be written as a total derivative, right? So is the derivative with respect to k of e to the I kt. Well, not quite, because that brings down an it. I only want a t, so I need a minus I. If I write a minus I here and do the derivative, this is exactly equal. Just check it. Alright, the derivative with respect to k brings down it, I times I is minus 1, minus is plus. So it's t e to the I kt. Wonderful, so I can substitute it here. This is 1 over root 2 pi integral minus infinity to infinity dt minus I d dk e to the I kt. Awesome. Now, that derivative with respect to k can jump the integral with respect to t. It's a different variable, right? So I'm integrating with respect to t. Okay, let's do it. So this thing is the minus I derivative with respect to k. Now, 1 over root 2 pi integral minus infinity to infinity dt e to the I kt. Oh, nice. What is this guy? Well, this guy is literally 2 pi delta of k, you see? K and the rho of k and t is swapped here, which is fine. It's a dummy variable, and the other is the variable that this thing depends on. So this is 2 pi delta of k, you see? All right, so if this is 2 pi delta of k, what I get when I do this transform is minus I, and then I get 2 pi divided by root 2 pi, so root 2 pi. And now I get derivative with respect to k of the delta of k, so delta prime of k, where the prime means first derivative. So the Fourier transform of t is the derivative of the delta. So if the delta was already weird, the derivative is more. It's something that is zero everywhere, right? Because the delta is zero everywhere, but then at 1 is more divergent. It's only infinity at 0, and then when it reaches 0, it's very divergent. The delta actually satisfies that it derivates in the integral sign. Prove it. Can you prove this? Integral of delta prime of t minus t0 f of t is actually equal to f of t0. That's what would happen if it were a delta, but because it's a prime, it derives it. It differentiates it. Try to prove it. It's not too difficult to prove. What you need to do is integration by parts, kind of. It's a challenge. Take it as an advanced program. Try to prove that. This is outside of the scope of the course, but you can see that we can make sense of the Fourier transform of functions that in principle shouldn't have a Fourier transform. But that's okay, because the Fourier transform of those functions is not a function, it's a distribution, like the delta is. All right? Now, that said, let me quickly erase and keep the definition of the delta, and let's try to understand the Fourier transform more based on this result. So we have the delta, definition of the delta, or the representation of the delta in terms of the orthonormal basis. The exponentials are an orthonormal basis for the space of functions. It's super interesting though, because the space of functions they represent, which is the space of integrable functions, they're not really one of the objects. This is, if you ever study quantum mechanics for real, not just at user level, but for real, interested in understanding the foundations and the math, you will see that. You will. These problems appear when you talk about eigenstates of position and eigenstate of momentum, states that are definite for a particle that have definite position or a definite momentum. They're really weird, and they're not part of the space of states. But still, they can form bases of the space of states. Again, you can ignore this comment just to instill a little bit of curiosity in those of you that may be interested in quantum mechanics, because you see, the weird things that everybody talks about in quantum mechanics, oh, it's dead and alive at the same time. Oh, you can know position and no momentum and at the same time. All those things are consequences of the math that's behind it. And this is the freaking math that's behind it. To a very low level, that said, we need to build way more to get there, but to a very low level, we see in the math that is responsible for all the weird physical interpretations of quantum mechanics. So hopefully that gives you, some of you who are interested in that, give you some motivation to learn more about this. In any case, let's understand what the Fourier transform of a constant is. So imagine that I want to do the Fourier transform of 1. Well, we already saw that, but let's do it again with the definition. So that would be 1 over root 2 pi integral minus infinity to infinity dt of 1 e to the I kt. This thing again is 2 pi delta of t. So what we get here is that this is the 2 pi cancels, so it's root 2 pi, right? It's root 2 pi delta of t. Delta of k. T cannot be t. This is not a function of t. T is integrated over. All right. K is the function. Wonderful. So, what I get now, if I represent it, is I have in time domain, I have a constant, and in the frequency domain, again, this is k, there's no oscillations, there's no change, it's a constant. Well, everything is 0, 0, 0, and there's only one contribution, is the delta at k equals 0. Indeed, there's the only frequency component is a DC component, which is 0 frequency, right? So indeed, the Fourier transform of a constant is a delta. All right, let's do the Fourier transform of the sine and the cosine, shall we? So we have here for reference the Fourier transform of 1. The next thing that we will do is the Fourier transform of e to the I omega t. e to the I omega t. What is the Fourier transform of that? The nice thing about that is that I can use the shifting property, the shifting the frequency domain. If you remember that property, that we let me just write that property here. That told me that the Fourier transform of e to the I omega t f of t is equal to e to the I to f of k plus omega. That's the shifting property. All right, but you see, this thing is the Fourier transform. Well, let me write it like that. The Fourier transform of e to the I omega t times 1. So what I get here is the Fourier transform of 1 only shifted by an amount omega. Okay, it's shifted by an amount omega. So it's evaluated at k plus omega. All right, so if I do that, what I get is root 2 pi of delta k plus omega. All right, so this is the Fourier transform of e to the I omega t. Wonderful. Now, if so, what this is telling me, well, I can do now the Fourier transform of the cosine, for example, omega t, because this is, remember, is the Fourier transform of e to the I omega t plus e to the minus I omega t divided by 2. That means that this is 1 over 2. Then Fourier transform of e to the I omega t. Well, if I add a minus here, let's do both at the same time. Plus minus, plus minus, plus minus, plus minus. That's what you get. When omega is, the omega is minus omega, you get a minus, right? The sine of omega. All right, so I get this plus the Fourier transform of e to the minus I omega t. All right, I can substitute, and what I get is root of pi divided by 2 that multiplies delta of k plus omega plus delta of k minus omega. Aha, so let's plot this. So of course the cosine has only one frequency, which is omega. Right, so if we plot the Fourier transform, it's 0 everywhere except for when k it's equal, this is k, and this is k equals to omega, and this is k equals to minus omega. So what we get is 0 always, and then a peak in k equals minus omega, 0 always, and then a peak to infinity when k equals plus omega. So we realize that the cosine only contains one single value for modulus k, which is omega. There's only one frequency of oscillation, only one, and it's k equals omega. It doesn't, it's just a cosine, it's a pure tone, a pure vibration, right? So there's only one frequency component, and we see it here. Now, you can say, why does it have also minus omega and plus omega? What's the meaning of the negative part of it? That's a really good question, and that's related with, it's related with right movers versus left movers and stationary waves. We're not going to talk too much about it, but keep in mind that this negative frequency part and this positive frequency part gives you the same kind of information. Basically, a real function has to have, that is oscillatory, has to have as many negative frequencies as positive frequencies, right? If it's stationary, right? That's what stationarity is giving you. The I omega t, the sum of a sine and a cosine, is the one that has only one peak that is positive. It's kind of telling you, in a way, a direction of oscillation, right? So, in a way, if it's oscillating like that or oscillating like that, and the sine and the cosine, both of them, you can think of them as oscillating like that or oscillating like that independently. So it contains a frequency of oscillation in one direction and in another. This is very rough and not rigorous, but at the level of math that we've seen, I think should be enough, and also to trigger a little bit of questions on your side for our review sessions. But you see how The Fourier transform is telling us the number of frequencies that there are in the function. At the end of the block, we're going to discuss a little bit about interpretation of the Fourier transform. All right, let's do the sign. Well, the sign is not that different. I'm going to do it right here. The sine omega t, is the Fourier transform, of course, of e to the I omega t minus e to the minus I omega t divided by 2. So what we get in the end is very similar. I get square root of pi over 2. Now I up to I thought I wrote it. Pi over 2 in there, but I have a 1 over I, or a minus I if you want, which is the same. Minus I. And then I get the sum of the delta of k plus omega minus the delta of k minus omega. So the plot is kind of similar. The only difference is that instead of having that one, I'm going to write it in another color, perhaps blue, if this works. I don't know if it will. It would be the same. Oh, yeah, it works, but so it would be the same here, the same arrow, okay, for the sign. But then the sign has a negative to infinity p there. So you see, if you sum the two, also it would be complex, right? It's nice. So in this case, for the sign, I need to plot ik. Right, the Fourier transform in general is complex. But you can tell that the modulus of the Fourier transform gives you information of how many frequencies contribute to my signal. We will talk about it in terms of music in a second, because this is what distinguishes, you see, we will talk about it, about what is the timbre of an instrument. How do you distinguish the same note as played by a saxophone and as played by a triangle or a piano, even if it's the same note? All right, so now that we've seen that, let's go a little bit into, before we see uncertainty principles, let's go a little bit into this kind of interpretation of the Fourier transform. All right, let's talk about two things. Let's talk about musical instruments, and let's talk about pictures. And I hope that I just give you a little bit of stimulus for us to discuss later on in class a little bit more about this, okay? So, of course, if you hit a tuning fork, or if you play a piano, play a saxophone, or you sing, even if you hit exactly the same note, you can distinguish, oh, that's a violin, that's a human singing, that's a saxophone, and that's a tuning fork. They're different. They have different timbre, even if they're playing the same notes. What distinguishes them? Now, those of you who have studied or seen anything about music, you would say, oh, the higher harmonics or whatever you want. But that, when musicians usually use, I mean, not people who study the physics of music, of course, but people who don't know much about music and say that, they don't really, it's just a bit rough. It's usually like a description of high harmonics, high vibrations, and so on. Very rough understanding without knowing what's the math behind it. Let's see what the math is behind it. Tuning fork. A tuning fork of a given frequency, say that it's playing, I don't know, red or something. Tuning fork, pure red. The tuning fork is very, very close to a cosine or a sine wave. So it's only one frequency almost. I mean, not quite, but almost. So the Fourier spectrum contains only one frequency. You would see something like this in the Fourier spectrum. In fact, you would plot only probably the positive one, but whatever. Plot the frequency spectrum, and then you get, and usually the modulus of the frequency spectrum, which is what you can measure most of the time. The frequency spectrum would be boom, going up, and then 0, and then going up only for the frequency of the tuning fork, the adaptation or tuning fork, whatever you want to call it. Now, what happens if we play the same note with a piano? Well, with a piano, the vibration of the string is not gonna, in the box and so on, it's not gonna look like that. It's gonna look like, with the same period and amplitude, that should be the same as here, because the same note. And if you do the Fourier transform, then you see that in the Fourier spectrum, this thing contains frequencies around that and around that. It would contain frequencies around the main frequency. Those are the higher harmonics, because it's not really only higher harmonics, because that's more a Fourier series kind of thing where you have a discrete number of frequencies. Here we have a continuum of frequencies, okay? Because yes, the string produces a continuum, because even the boxes that don't, the harmonics that don't resonate with the box, that is the piano, escape the piano and give contributions. Of course, you're gonna have not like that. You're gonna get little small peaks at the higher harmonics as you go, which are the ones that actually resonate with the cavity, and it would be peaked like that, which is equally spaced, which are the ones that resonate with the cavity, right? And in these frequencies and in these peaks is the information about the sound. So the timbre is the shape, the waveform, not the period of the average period of the wave. It's the waveform, the shape of the form. That is actually how many different Fourier components the signal contains. Now, this is also used for compressing information like JPEG and things like that in a picture. So a picture, if you want, I mean, let's think of a black and white picture in order to make it simpler first. For a black and white picture, it's a function, let's say of two variables, that basically tells you how strong a pixel is. It says maximum is black. Let's say if it's 1 is black, if it's 0 is white, for example. Now, that function you can transform to the Fourier spectrum. And it's super cool because in the Fourier spectrum, the information that is contained, let's see, high frequency versus low frequency. So if the picture is, say, the picture of a building, something like that with the windows, please, well, excuse my drawing skills, and some door, or whatever, and then landscape. Here I'm gonna get a pyramid, why not? With some other set of gates and something like that, and then a person and the clouds and a tree and things like that. A picture like that, okay. And then like the bricks or whatever makes the pyramid and so on. Now, the Fourier transform would contain, I'm not gonna faithfully represent what the Fourier transform would be, but we contain information here and there, high frequencies and low frequencies. What happens if I cut? So what is the information stored in the low frequencies? The information stored in the low frequencies is, remember, low frequencies implies long wavelength. Is the shape, the rough shape, the information. If I filter out, imagine I do the Fourier transform and I filter out the high frequencies, when I reconstruct, and then I do the inverse transform, when I reconstruct the picture will be something like this roughly. Kind of the shape, I mean with the right proportions, right? But I would miss the tree, I would miss the person, certainly not the windows, certainly not the bricks. The information about small things is contained on the high frequencies. The high sampling, I need to sample a lot in order to see, I need to sample a lot here to see the difference on the window. Low frequencies is just sampling roughly, coarse grained, and just getting the shape of things. Interesting enough, I can make it blurry. How do you make it blurry? When you ask Photoshop to make something blurry, what it's doing is the convolution of the Fourier transform, then the convolution with the Fourier transform of a Gaussian, which is a Gaussian, and then transform back. That blurs everything. The frequency spectrum contains, so here all the information is mixed in the space domain. If we go to the frequency domain, we have the low detail, the shapes, and the high resolution detail, the windows and the doors in the high frequency. If I cut the low frequencies but I keep the high frequencies, I will get a mess of details that doesn't have any form or shape, just the scale of the details. Now, JPEG, and among other doing other things, because it's based on fractal algorithms and so on, but some of the things that you do is move to the Fourier spectrum and cut the frequencies, like the really low, like high resolution I can cut and replace by a fractal pattern and do other things. That is actually pretty cool how JPEG works. I'm talking about advanced JPEG and other implementations like that. But manipulations in the frequency spectrum can actually be used to efficiently compress by removing more information about details we don't get to see, because they're in the very small detail, fine structure of the picture that the eye will not perceive. Okay. Anyway, I hope that this kind of triggers a little bit of discussion for later on in the live sessions for us to discuss, because I think that on video it's very difficult to transmit all that. All right. Now, let's see one more thing. Let's see a little bit about the uncertainty principle. That is also an exercise. That could be an assignment exercise, right? We're going to do the Fourier transform of a Gaussian, and we're going to discuss something that we already saw with the scaling property of the Fourier transform. The scaling property told us that if I make something sharper, like thinner, in the time domain, it would become wider in the frequency domain, and vice versa. All right, so let's see this. Okay, the Fourier transform of a Gaussian function and the uncertainty principles. Now first, what is a Gaussian function? Gaussian functions are things that look like this. So you see, minus y squared, where y is the variable, divided by something that I write as 2 delta squared. Now for a function like this delta here is what we call the standard deviation, and it's the width of the Gaussian. It's basically telling you the width of the Gaussian. All right? Okay. We're going to use this exercise. This is a given that the integral of from minus infinity to infinity of e to the minus x squared is square root of pi. You can check it will go from alpha, and you can do it yourself to practice, okay? But this is something that we're going to use as a result here for this exercise. Now, I write a Gaussian here, this one, f of x, our targets function, the function that we want to Fourier transform, is a normalized Gaussian. You can check by using this identity that the integral of this function from minus infinity to infinity is 1. So it's a normalized Gaussian. This is what is called a bell curve, a probability distribution that appears when you have a sufficiently large number of random samples. That's something really cool about it. I will tell you about those things in the next video, a little bit about a little bit more advanced mathematical notions related to these things. Anyway, this Gaussian that I wrote, which is a bell curve, not what professors do when they say the bell curve, because usually bell curving means just translating towards the right, the distribution of marks, not bell curving for real. Anyway, there's a bell curve for real, its integral is 1, and I want to compute the Fourier transform of x. Now notice that the Fourier variable that I'm using here is p instead of k. X and p. X is the U1 position variable, and p is the frequency domain of x. Maybe linear momentum, which is what it is. Anyway, whatever. We will talk about that later. It's just for dramatic purposes that I call it P, okay? You will see the reveal at the end and the drama, like, oh. So for that I need to be calling it P, right, to make it easier. Anyway, so let's compute the Fourier transform of f of x. The Fourier transform is this, when the constant factor comes out of the Fourier transform, and I get the Fourier transform of e to the minus x squared over 2 sigma squared. Now, I realize the following. If I define, let me just write it here, if I define a g of x, which is this normalized Gaussian that I have there, e to the minus x squared, just that, then I realize that e to the minus x squared divided by 2 sigma squared is nothing but g of x over 2 sigma. If I substitute where I see an x here, I write x over 2 sigma, I get exactly that. So it's a rescaling. So if we remember, I'm going to erase it in a second, but let's remember just for a little bit the scaling property of the Fourier transform. The scaling property tells me that if I have the Fourier transform of a g of r x, then I get 1 over the modulus of r, right, times the Fourier transform of g x over r. Well, in our case, r is 1 over 2 sigma. So we can use the scaling property and say that the Fourier transform of g x over 2 sigma is equal to 2 sigma Fourier transform of g 2 sigma p. Sorry, this is p, not x, my bad. It's the Fourier variable. Sorry about that. All right, because this thing is exactly what I'm looking for, what I'm going to write here is the constant factor 1 over 2 sigma root of pi 2 sigma from here g of 2 sigma p. All right, I can erase this now because I've already used it. This is using the scaling property. Remember, right, the scaling property tells us that if you scale the function in the time domain, in the frequency domain, if you widen the time domain, it's going to shrink in the frequency domain. We're getting there. All right, so this simplifies, of course, and what I'm left with is that f of p, the result I'm looking for, would be 1 over root pi g of 2 sigma p. Okay? So now our objective is just to find g of p. If we have g of p, we can substitute in here and we get it. G of p is the Fourier transform of the simpler Gaussian e to the minus x squared. Now it's simpler, but it's not extremely simple. Let's do it and follow me because there are some cool steps going on here. How we solve this. There are many ways of solving this. I'm just taking one that uses Feynman's trick. All right, let me write the definition. So the definition is 1 over root 2 pi from up there, right? Integral from minus infinity to infinity dx e to the minus x squared and e to the I px. All right. The first thing that I'm going to do is I'm going to differentiate on both sides of the equation. If I do that, on the left I get d dp g of p. I take a derivative and I'm going to take a derivative on the right. Now, realize there's no p until I hit this, right? So the d dp of the whole thing can come into the integral because the integral is with respect to x, which is a different dummy variable than the p in here. So I can jump in with the derivative into the integral, differentiate under the integral sign, and then I get 1 over root 2 pi integral minus infinity to infinity dx e to the minus x squared d dp e to the I px. Now this is an easy integral. This thing is just, with respect to p is ix e to the I px, right? This is what it is. Yeah, let's just substitute by it. All right, so we get that. Now, I'm gonna erase a little bit of this because I need it. Now, one thing that we can realize, okay, let's realize something. So let's write a wormhole here and write a realization here. So now we go into the wormhole, we will appear somewhere else. And in the meantime, let's realize something. What is the derivative with respect to x of e to the minus x squared? Well, glad that you asked. That is just simply 2x e to the minus x squared. We know how to derive, right? To differentiate. Wonderful. But that also means that e to the minus x squared is equal to minus 1 divided by 2x derivative with respect to x e to the minus x squared, right? All that I did here is move this to the left hand side. Let's do that substitution at the outside of the wormhole. If we do that substitution, we get g of p on the left hand side with a dot because it's the derivative of g of p, so g dot of p is equal to. Now, let's take the I outside and I get I over root 2 pi, okay? And I get the integral minus infinity to infinity dx. And now I substitute minus e to the minus x squared, it's equal to minus 1 over 2x derivative with respect to x of e to the minus x squared. Wonderful. Then I get an x that I haven't moved, and it's inside the integral, cannot come out, e to the I px. But then I realize, this x cancels this x, and I can take the minus 1. So I get g dot of p. I can take the minus 1 out, and I get minus I divided by 2 root 2 pi. Okay, then I get that there. And then I get the integral from minus infinity to infinity dx dx e to the minus x squared e to the I px. Why did I do that? Why is it useful to do that? How am I supposed to come up with that idea? Well, because what I want, the integral that I know how to do is the integral of minus x squared e to the minus x squared. It's a difficult integral. There's no antiderivative for that. That is kind of that's the error function. So, yeah, the antiderivative of this e to the minus x squared is difficult. So what I did is I was ingenious enough to write it in terms of a derivative, and therefore I can do integration by parts to integrate this directly. How? Well, all that I have to do now, let's do by parts integration. dv, it's equal to dx dx e to the minus x squared. So v is just the integral cancels the derivative e to the minus x squared. Nice. And then that means that u is equal to e to the ipx, and that means that du is equal to e to the ip e to the ipx dx. We implement the by parts integration now, and we get, let's write it, g dot of p, it's equal to, the constant is the same, minus I to root 2 pi. All right, and that multiplies. U times v, so e to the ipx times e to the minus x squared, from minus infinity to infinity, minus integral from minus infinity to infinity. Now I write dv, so du, so dx, ip, and now e to the ipx, and then I write v, e to the minus x squared. Wonderful. So what I do now is realize that this at infinity is e to the minus x squared, at infinity is 0, and minus infinity is also 0. This thing cancels. So when I'm left with the minus and the minus cancels, but then I have an I times an I that gives me a minus sign. So let's do a wormhole. And let's erase this because we don't need it anymore, we already used it. And the wormhole that opens here, g dot of p, it's equal, again, let's write it, the I and the I are minus, and the minus and minus are plus. So we have a minus p, the p can come out because it's an integral with respect to x, so can come out, divided by 2 root 2 pi, and now integral of, from minus infinity to infinity, dx of e to the minus x squared, e to the ipx. Wonderful! Have we won? Well, not quite yet, because we've recovered again the original integral we wanted to solve. That's not bad though. So this thing is square root of 2 pi, the Fourier transform of g, right? It's gk. Right? Sorry, brief GP. Right? GP is exactly that with 1 over root 2 pi. So this thing is root 2 pi times g of p. Wonderful. The root 2 pi cancels. And what I'm left with is g dot of p equals minus p divided by 2. Alright? Times g of p. And I can erase that now. Now, what is this? This is a differential equation, right? And it's a differential equation of the kind we know how to solve. This thing is a separable differential equation, the simplest possible kind, right? Minus p divided by 2. And that thing, integrated on both sides, gives me a log. I mean, we've done 1,000 of these. This gives me, I don't need this anymore. I'm going to write the 0 there. This gives me the log of g of p equals 2, and here I have to integrate, and the integral gives me p squared divided by 2, so minus p squared divided by 4. All right, wonderful. That's integrated on both sides, integrating with respect to p. Wonderful. So I take x, well, plus a constant, let's call it d. I take the exponential on both sides. Let's open another wormhole. This one's special. Taking exponential on both sides, the first one, and that's the log. And I get this as a constant, which is, I'm calling it c, the exponential of d, right? Exponential, like the same ones we've been doing all day. Exponential of p squared divided by 4. All right, all that we are left to find is g of p. Oh, sorry, it's the constant c. We get g of p except for a constant. How do we find that? To determine the constant, we realize that g of 0 is, on the one hand, well, it's the constant, right? Because when p is 0, it's just the constant. But on the other hand, is this, so where is it? G of p is this definition, When p is 0, it's just putting a 0 in here, right? So writing the definition with the Fourier transform, we get that this is equal to 1 over root 2 pi integral from minus infinity to infinity dx e to the minus x squared e to the I 0x, so 0 which is 1, that's just an integral. So these two things are the same. And I know what this integral is because that's the help that I was given. So this is c, it's equal to 1 over root 2 pi times root pi, which is equal to 1 over root 2. That is what is c. Finally, we found g of p. G of p, it's equal to 1 root 2 e to the minus 1 over 4 p squared. Wonderful. Now that we have the result, let's erase all the derivation, put the result there, and solve f of p, which is what we want. E of p is 1 over root 2 e to the minus p squared over 4 that we had over there. Now we just need to substitute in here. So that means that f of p, which is equal to 1 on root pi. Now I copy g, 1 over root 2. And now I get e to the, whenever I see a p, I write 2 sigma p minus p squared. So p squared would be 2 sigma p squared divided by 4. Simplifying, I get 1 over root 2 pi exponential, the 2 squared cancels the 4 of minus sigma squared p squared. Wonderful. All right, so this is the final result in terms of getting the Fourier transform of f of p. This is the result, right? Let's analyze what happens with the width of these two things, shall we? All right, first, let's plot here the first Gaussian, f of x. So the first Gaussian has a width sigma, right? We can compare delta is literally sigma here. So sigma is the way this is supposed to be symmetric, you know, like drawing skills. I don't know if it's more symmetric, but okay, hopefully you get the idea. That's f of x. What's the width now of f of p? Well, it's another Gaussian. That's interesting because you see the Fourier transform of a Gaussian is another Gaussian. The Gaussian is the only function that the Fourier transform is of the same kind. It's another Gaussian. Notice as well that the Gaussian is an ascent delta, right? The area under this bell curve is 1, which means that if I make it thinner and thinner and thinner, it gets taller and taller and taller. The area is 1, concentrates in one point and gives you a delta, a Dirac delta in the limit of sigma going to 0. All right, that's the Gaussian with respect to x. Let's see what is the Gaussian with respect to p. So if we write e to the minus sigma squared p squared as e to the minus p squared divided by 2 delta squared to know the width, we realize that delta is equal to 1 over 2 sigma, right? If you substitute 1 over 2 sigma in here, the 2 cancels the 2, the sigma is 1 over sigma over 1 over, which goes to the numerator, okay? So delta in this case is 1 over 2 sigma. That means that in momentum space, this other Gaussian, which is the Fourier transform of the Gaussian in position space, has a width of 1 over 2 sigma. Ha! Let's think about it. Well, one thing that is clear is that if this is wider, if I increase sigma, I decrease the width of this distribution on P. Imagine that this is an experimental distribution that I get out of measuring the position of a particle. And I get some experimental error. It's mostly here, but sometimes I measure it here with some error and then decays like that. So what is the uncertainty I have in momentum? Look at the law, the nice law that they satisfy. If we call this thing delta of x and this thing delta of p, so the uncertainty in position, the uncertainty in momentum, they satisfy, multiplying the two, that, well, what is this? This is sigma times 1 over 2 sigma equals 1 over 2. Oh my goodness, delta x, delta p equals 1 over 2. That means that if you know the position with full precision, which is the limit when this is a delta, all the probability distribution of finding x is concentrated in a point, That means that the momentum distribution is infinitely wide. So we don't know the momentum that the particle has. On the other hand, if we know exactly the momentum that the particle has, with a lot of precision, we get a very narrow distribution here, knowing very well what the value is. The probability is very high to get in one single value. Then the position distribution gets super wide, which means that I have no idea where the particle is. It's everywhere to all effects. This is what's behind Heisenberg uncertainty principle. That would happen, you remember, this is position and momentum, but it's also true for time and frequencies, right? Remember, times and frequencies are also Fourier conjugate variables, same as position and momentum. Interesting enough, this is for Gaussians. Gaussians are the ones that saturate this. In general, for any other function, you always have that is larger or equal, so it's worse than the Gaussian. The Gaussian is the one that is the best, as keeping, for the smallest position spread, the smallest position momentum, the smallest momentum spread as well. And yet, if I make this 0, the error in x, then the error in p has to be super high to compensate for it. What is more? This I did without units, right? X and p have no dimension. If I put physical units, this is position times momentum. The units of position times momentum are units of energy times time. You know what fundamental constant has units of energy times time? Another distortion of space-time. That's because I was to summon Planck. Planck constant. Yeah, that is the universal constant that has units of time times energy. Wow. So yeah, when you put units in it, you recover the famous Heisenberg uncertainty principle. When you know with full precision the position of a particle, you have no idea of its momentum. If you determine fully the position, the momentum, the position of the particle is completely localized. Particle is everywhere. So you see with this, that many of the things that people talk about intuitively and do a lot of philosophy and so on in quantum mechanics, like the uncertainty principle, they actually come from the math that you need to describe the physics. Now, at some point, people realized, well, to describe the experiments we have no option other than talk about the wave function, and then these functions, the Fourier transform appears naturally. If it is position, the Fourier transform is the momentum, and so on. Well, if you do that, then you have to pay the price that you have to live with uncertainty principles like this. So these consequences, these neat effects in physics that everybody talks about and awes about, like marvels about, they are a consequence of the math that we need to describe the universe. So that's how they appear, through these Fourier transforms, through the math that's behind Fourier transforms. It so happens that the universe behaves like Fourier transforms. The Fourier transforms are the language in which we write that behavior of the universe too. That happens every time that in signal processing or anything, every time that you go from a time domain to a frequency domain, you have an uncertainty principle. If you know the time, you don't know the frequency. If you know the frequency, you know the time, with a balance between the uncertainty in the two. I mean, that you don't know is the width in frequency. If the width in time, if it's a very short pulse, it's got all the frequencies. It's made up of all the frequencies and all the energies. If it's only one frequency, then it has to live forever. Like the cosine. The cosine is only one frequency, right? As we saw, only one frequency. Well, how long is it in time? The cosine stays there forever. Any signal that starts at time equals something, equals t equals 0, for example, anything that starts and ends has to contain more than one frequency because of the uncertainty principle. All right, wonderful. So I hope that this inspires you. If you ever want to know more about quantum or uncertainty principles, it's very similar to many of the things that appear in signal processing, that particular bit of quantum. This is basic quantum stuff. It's not very complicated. Now you know the math to deal with it, no problem. I hope that this kind of inspires you, and we can have more discussions in the review sessions, and maybe if you're interested in these things, you can take more courses that relate to this. Anyway, that's almost all about the Fourier transform. We're going to see one more thing, which is the relationship with the Laplace transform and relationship between calculus and algebra. But that's going to be in an independent video to relax a little bit, because that's not material that you will be examined of. And with that other video, we will finish the blocking of Fourier transforms. All right, I'll see you in the next video then. Happy uncertainty principle.